So Friday we looked at composite functions and how we get composite functions. And what they want us to do here is to express functions as composites. In other words, what we're going to do is they have a composite function here, and so we want to write the two functions that make up that composite function. Okay? In other words, h of x here is equal to f of g of x. So I need to find f and g. And I can't do it by excuse me, by letting one of them be just x. It has to be something other than that. So what we can do is a couple different things. Now, we could take and just this function 3x squared plus 1, so I could have the square root of x, so it would be my f of x, and then my g of x, 3x squared plus 1. So if I did f of g of x here, I would get this composite function, square root of 3x squared plus 1. All right, can you see that? Obviously, no. This is our composite function. So we need to find two functions that when I do the composite, I get this. One example is here. We could let f of x be the square root of x, and then g of x could be 3x squared plus 1. So if I did the composite of them, the 3x squared plus 1 would replace the x, and I would have the square root of 3x squared plus 1. Okay. They could be. Okay. They aren't necessarily dependent on who the individual is, but they could be. Okay, so let's think of a different way to do it. Okay. What else could I do? I kind of put something green here, but we'll cover it. We'll get rid of that. You can see it now. So f of x equals and g of x equals. Yes, Gallery. All right, let's try it. Square root of 3x. Okay. Let's check that out. All right. So if I took this, okay, and I put it in here for x, right, because that's what the composite function is. 3 times x squared would be 3x squared, and 3 times 1/3 is 1. That would work. Okay, good. All right. How about a different one? Yeah. No, you can't do that. No. I mean, the easiest one would be to say that f of x equals x, and g of x is the square root of 3x squared plus 1. Okay. All right. But you can't use the identity, what they call the identity function. You can't just use x. All right. You'd have to find something else. Can anybody find a different one? Okay. There's at least one more that I know of. That's a good one. Something x plus 1. So if you had g of x be x plus 1, or how about, or f of x be x plus 1? Okay. Would we use the square root with that? Okay. So let's look at this then. All right. So let's kind of take what Sierra's talking about here. And let's say that one. All right, so f of x equals square root of x plus 1. All right. What could g of x be then? Okay. All right. And so David says g of x could be 3x squared. Okay, would that work? Okay, because we're just taking the 3x squared, putting it in there for x, and that would work. Good. All right. All right, some teamwork that helps. Okay. All right, that was the second one that I had. All right. And sometimes there's not many of them to look at, but in this case, we found 3 different ones we could use. We've got, oops. All right. So there's 3 different ones that we could use for this, to do this composite function. All right, so let's look at the example that you had. All right. H of x equals the square root of x cubed minus 5. So we want to do f of g, so h of x equals f of g of x, or f of g of x. Okay. So what's one example of this we could use? Okay. Okay, that would work. Square root of x and then x cubed minus 5. So we're just going to replace this x with x cubed minus 5. All right, good. How about another one? Rachel? What? Okay, good. All right, those are the 2 basic ones right there. Square root of x and x cubed minus 5. Okay, so x cubed minus 5 is going to go in for x. Or square root of x minus 5, and then we're just going to replace the x with x cubed. Okay. Yes?
Are you multiplying the g of x equation with x, or are you just putting what the g of x is?
We're doing a composite function, which means we're replacing x with the other function. Okay? So we're replacing this x and f of x with all of this from g of x. Okay? That's what the composite is. Okay? Don't even push it. Okay? All right, can you see it a little bit? Okay. Stop. All right. Okay. All right, number 6. A cylindrical container is being filled with water, or filled with water in this case. After t minutes, the height of the water in the container is h of t equals 1/2 t plus 3 inches. The volume of the water in the container is given by v of h, which equals pi over 4 h cubed. So we have the height of the water in the container is 1/2 t plus 3. That's how it's changing. The volume is changing by pi over 4 times h cubed. They want us to express the volume as a function of time and compute the volume after 2 minutes. So if you notice, okay, this says h of t equals, all right, with respect to t, and t is usually time. This part, v of h, is in respect to h, okay, the height, not the volume, not the time. And so they want us to use a composite function then that will express the volume as a change in time. So we just need to take and put 1/2 t plus 3 in for h. Because h equals 1/2 t plus 3, so I'm just going to replace that h with 1/2 t plus 3. And right now then, they want us to find the composite. We're not going to actually cube that function. We'll just leave it as that. And then we want to find the volume after 2 minutes, right? Okay. All right. Oops, excuse me. So this is now v of t. So that would be pi over 4 times 1/2 times 2 plus 3, that whole thing cubed. Yes, we're just going to put 2 in for t then. Okay. So we get 1 plus 3 is 4. 4 cubed is 64. Okay. So this would be pi over 4 times 64, which is 16 pi. And this would be in what kind of dimensions? Or what would be our units? Something cubed. What is cubed? Right? Volume. 3-dimensional. Inches. Okay. All right. All right. 16 pi cubic inches, because we're dealing with our height is in inches, and so that tells us our unit is going to be in inches. 16 pi is around 51. Right. 3 times 16 is 48, and then 0.14 times 16, so maybe it's 49 something. Okay. All right. And then we had a couple of them from 3.6, inverse functions. What do we know about inverse functions? It's not the opposite. Kind of reverse. We do what, Emily? Switch the x's and the y's, all right? So when we talk about an inverse function or an inverse relation, we're talking about taking the values of x and switching them with the values of y. So we have a reflection over the line y equals x. Well, what happens then is in certain situations then, so for instance, here's a situation that involves a world population. Okay? And it talks about the years with the world population. So if we were working with the inverses, then population would be on the x-axis, and the time or the years would be on the y-axis. So we would end up setting up a function or an equation that would find the year when we know the population. Well, we know how to do that. We've done problems like that before where we just graph them or solve logarithmic problems if we end up in those situations. So we're going to look at doing inverses. So a reminder we have here. The result of exchanging input and output values of a function or relation is called an inverse relation, which we talked about that. So when we switch the x and y's, we're talking about switching the inputs and the outputs. So if we graphed, so we have the graph of a function shown. They asked us to graph the inverse and describe the relationship between them. So your inverse will look like this, and the relationship is that it's a reflection over the line y equals x. So how did I plot that the inverse? Okay, we just, in every point, yep, switch the values of x and y and graph them. So I could, so the point -3, -4, we did point -4, -3, so that would go there. The point -4, -3 would be this point, -3, -4. Point -2, -3 would be -3, -2. So that would be here. This one here is -5, 0. So it would be at 0, -5. This one here is at -1, 0. So it would be at 0, -1. All right. And then we would have here at 5, 0 and at 5, -6. Okay. Is that a function? Is that inverse a function? No, it's not, because it fails the vertical line test. Good. Okay. All right. All right. Now, in exercise 55, if we get to it, shows that the line y equals x is the perpendicular bisector of the segment from AB to BA. In other words, if we have 2 points, we go back here, look at these for a second. Okay. These 2 points here at 5, 0 and 0, 5, the line y equals x is a perpendicular bisector. What does it mean to be a perpendicular bisector? What, Savannah? Crosses a 90-degree angle, and what else? So what does it tell me about? There's 2 segments there, right? Okay. It cuts it in half. It's a 90-degree angle, but the distance from the line y equals x to each point is going to be the same. Okay. So there's a caution that says when using a calculator to verify the inverse is a reflection over the line y equals x, it's important to use a square viewing window. In other words, make sure that your increments go the same both directions. Okay. Graphs of inverse relations. Well, we learned how to do parametric equations, right? If we're just doing switching x and y, then you could use parametric equations to write the inverse and to be able to graph an inverse. Does anybody remember how your calculator does it without doing that? I think I showed you that if you were in my class. Anybody remember? All right, so let's take let's use a simple one first of all. Okay. Yep. All right, just graph x squared. Now, if you go to second program where it says draw, second program to get to the draw, and down to number 8, it will draw the inverse. So if you hit enter, and then we're doing the inverse of y1, right? We have to put in which function it is we're doing the inverse of. So if you go to alpha trace, all of your y's are there. Okay, alpha trace, all the y's are there. Put in y1, hit enter, and it will graph the line and the inverse, which my window is not very good, so I'm going to go to zoom 6. And there's the graph, and I need to tell it to do the inverse again. There we go. Okay, so there it graphed the function and its inverse. Now we can also do that by using parametric equations. The problem with using this draw inverse on our paper or on our calculator is the fact that if I go to the table now, I still only have one table there, because the draw inverse, it doesn't give me any numbers for it, it just draws it for you so you can see it. Okay, just tells you where it's at. But if we go into parametric mode, it's much easier. So let's look at this in parametric then. It says graph this function and its inverse in parametric mode. So it's an f of x, so it's a y equals function. So they tell us that when we looked at parametrics before, it said, okay, so if I've got a y equals, that we're talking about right here, if we've got y equals, and in parametric mode, we're going to let x sub 1 equal t, and y sub 1 will be the function f of t. So x equals t, and y equals 0.9 t squared plus 0.1 t to the fourth. Oops, that's t to the fifth, not t squared. Minus 0.4 t cubed plus t minus 1. There's our function. And to do the inverse, we just switch x and y. So x would be 0.9 t to the fifth plus 0.1 t to the fourth minus 0.4 t cubed plus t minus 1, and y would be t. So the function that we would do, x equals t, y equals the function. To get the inverse, we let x equal the function and y equal t. All right, so let's graph it and see if we can get this to graph correctly. So first we got to change our mode to parametric. Put in t for x sub 1, 0.9 t to the fifth plus 0.1 t to the fourth minus 0.4 t cubed plus t minus 1. All right, let's just graph that first of all. Make sure we have that completely graphed. All right. Check our window first of all, negative 10 to 14. That'll be plenty. Let's try negative 5 to 5, see what we get. We might have to make some adjustments to our window to be able to see it. Let's see what happens when I graph this. Okay. All right. Now, what degree is our function? Fifth degree, right? So we expect, because it's an odd degree function, we expect it's going to start either a negative infinity or positive infinity, go up to the other, go the other way. Okay? So could this be the complete graph of it? Would that be sufficient for me? Okay. All right. Yes, it could. Okay. All right. So if we do the inverse then, go to our y equals. Now, you want to know the quick way to do this, right? What? Okay, copy and paste. Right. Or what I could do is I can go to my alpha trace, and notice now when I go to alpha trace, what do I see? It's the parametric ones are there now, right? Not just x, not y1, y2, y3, yes.
Okay, my graph is like half of that.
Okay, change your window. You need some negative values for t. Negative 5 to 5. Now I could put in for x sub 2t, I could put in y sub 1. Isn't that what we're doing, right? We're switching x and y. And then for y, I could just put, I can put the t in there, which will be faster. Okay? I could do it either way. So instead of having to retype that all out, I can just say, hey, this is the function I want there. Now let's see what happens when I graph it. Okay. Are those inverses? Oh, let's see. How would I graph the line y equals x on parametric? Well, I want all the values the same, right? When x is 5, y is 5. When x is 3, y is 3. So what would I have to have x and y both be? They would just be t, okay? Just the letter t. Both of them would be t, because I want them to change at the same rate. And I could make my graph do something different so I could see it better. So let's make this a dotted line, right? And graph it. Nope, still doesn't look dotted, all right? But does it look like that's a reflection? Okay. All right. So we can graph functions and their inverses using parametric mode where we can't necessarily do it as easily in function mode. If it's in function mode, I can just graph it and then take points, switch them, and draw the line. But in parametric mode, it allows us to be able to do it much easier as far as graphing is concerned. Okay. So here's my function, and here's the inverse. Is this inverse a function? In this case, is this a function? Let me get rid of the line y equals x. There's the function. Is that inverse a function? Yes, it is. Okay. All right. Okay, number 3. So I have a function rule here, f of x equals 2x plus 1. How do I find the inverse? What do we do? Switch x and y and solve for y. Okay, good. All right. So that'll give us g of x here. We switched x and y. I put x in for f of x, put y in for x. Solve for y, subtract 1, divide by 2. Notice that I wrote it as 2 separate parts. Okay, so make sure you do that. If you have a fraction, don't leave it as x minus 1 over 2. That 2 belongs to the 2 separate parts because it gives me the slope and the y-intercept then, so I know exactly what they are. Okay. And the inverse of a linear function is a function, so I can call it g of x. If it was not a function, then you would just say y equals. Okay. Any questions on that? On those? So inverses, just switching x and y. Okay. All right. And finishing some work with the composite functions.